We've already looked at multiple events occurring, and all of those examples had the events occurring at effectively the same time. They were being considered together, tossing 2 coins and looking at the results overall. Tossing 3 coins, looking at the results overall, rolling 2 die and adding the totals together. But what if we have separate events that are occurring one then the other? Especially if, in some cases, the outcome of the first event might influence the second event. In cases like this, we have to consider the options differently. It is especially important that we consider events happening one than the other, like this, if we do not necessarily have equally likely outcomes. With the 2 coin tosses, both coins had equally likely outcomes. With the 3 coin tosses, all 3 coins had equally likely outcomes, and with the 2 die, each die had equally likely outcomes. Best explained with an example though, so let's have a look at one to start with. A bag contains 6 red counters and 4 blue counters. A counter is chosen from the bag at random. Its colour is recorded and the counter is replaced. A second counter is then chosen. So the idea is we go into the bag, we've got a bag of counters, we pick a counter out of the bag, it's either going to be a red or it's going to be a blue. We look at it, we notice whether it's red or blue, we put it back. We then pick another one out. The second one is either going to be red or blue. We could look at the chances of these. There will be a certain chance that we'll get a red then a red, a certain chance that we'll get a blue then a blue, a certain chance that we'll get a red then a blue, and a certain chance that we'll get a blue then a red. Now notice in particular there are different numbers of red and blue counters. The chance of getting a red is not the same as the chance of getting a blue. We do not have equally likely outcomes. So we can't just list the different options, because really there aren't 4 options. It's not that we've got red, red, blue, blue, red, blue, blue, red. We haven't just got those 4 options. We've got lots more than that, because there are 6 different red counters and 4 different blue counters. It would take us a long time to list all of the options. So we're going to do something else. We're going to draw what's called a probability tree. First thing we're going to notice in this question, we're going to notice the single most important piece of information in this question, and that is this, that the counter is replaced. That means that we are dealing with the same number of counters on the first pick and the same number of counters on the second pick. The number of counters and the counters that are in the bag do not change between the 2 picks. Sometimes they might. In this particular question, they don't. So we're going to think first of all about the first pick, and we're going to draw the first branches on our tree. The idea is we're going to have the branches giving us the different options and combinations. So the first thing we're going to think about, we're going to think about that first pick. And that first pick has 2 options. On that first pick, we could either get a red or we could get a blue. They are our 2 different options. On the branch then, on the line, we are then going to write down the probability, the chance of getting each of those options. There are 6 red and 4 blue, so that's 10 counters overall. 6 of them are red, so we have a 6 out of 10 chance of getting a red counter on that first pick. 10 counters overall, 4 of them are blue, so we have a 4 out of 10 chance of getting blue on the first pick. Something to notice at this point, 6 out of 10 and 4 out of 10, if we add those together, we get 10 out of 10 or 1. That makes sense because the 2 options are red and blue. That's all the possible options, and the possibilities. If we have all the possible options, the probabilities will add to 1. It's a useful thing that can be helpful to check our answers on these branches. Now, we've taken our first counter out. It was either red or it was blue. We've looked at it, we've noted what it was, we've put it back. We then need to make our second pick. But our second pick does, to a certain extent, depend on what our first pick was. Let's imagine, first of all, that our first counter out of the bag was red. So we're going to be looking at the top half of this tree. The second counter could then be either red or blue. But we have to be doing this as if we got a red on the first option. So we're going to have 2 branches coming off the red, giving us red and blue as our options. If we were to follow the branches then, if we were to follow red then red, or red then blue, we could get 2 of our possible combinations. we need to think about the probabilities again. We need to write the probabilities on the branch. Well, because the counter was put back, the probabilities for the second pick are exactly the same as the ones for the first pick. So 6 out of 10 for the red and 4 out of 10 for the blue. If we hadn't put the counter back, the probabilities would be different because we'd have different numbers of counters. But we have put the counter back, so the probabilities are the same. We're going to leave that branch B for the moment because we're just making the 2 picks. Imagine now that the first counter out of the bag wasn't red but blue. So we need to look at the options after that. If the first counter was blue, we noticed it was blue, we put it back. We then have 2 options for the second counter coming off there. So we're going to draw 2 branches coming off the blue. This is us assuming now that blue was our first pick. That second counter could either be red or blue. And once again, the probabilities are the same. There's still the 10 counters in the bag. There's still 6 red and there's still 4 blue. So 6 out of 10 and 4 out of 10. So now, again, by following the branches, we can track the different possibilities. Red, 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 blue, blue then red, and blue then blue. But what do we do with all these probabilities? Well, it turns out that we can consider these different options. For example, we might want to work out the probability of getting a red, then a red. For reasons that are actually very difficult to prove, it turns out that we can find the probability of a red, then a red, by looking at the numbers along those branches, red for the first one, red for the second one, taking those 2 fractions and multiplying them together. Again, very difficult to prove why, but it does work. It will give us the final probabilities. And this can be proven. It can be proven by experimentation. Doing this as an actual physical experiment enough times will retrieve these results. So if we do 6 over 10 times 6 over 10, well, thinking back to multiplying fractions, we times the 2 top numbers together to give us the number on the top, times the 2 bottom numbers together to give us the number on the bottom. So we get 6 times 6 on the top and 10 times 10 on the bottom, giving us a fraction of 36 out of 100. We can do the same for red, then blue. So by following the branches. So probability of red, then blue, we're going to have 6 over 10 for the red, and then 4 over 10 for the blue. We're going to times those together. 6 times 4 on the top, 10 times 10 on the bottom, 24 out of 100. We could do the same for blue, then red. So probability of blue and then a red would be 4 over 10 times 6 over 10, following those branches, giving us, again, 24 out of 100. These 2 in the middle, they're not necessarily always going to be the same. A lot of the time they will be, but they are not necessarily always going to be the same. It depends what happens with, for example, counters in the bag. Final one, we can fill in probability of blue, then blue. Well, that will be 4 over 10 times the 4 over 10, giving us 4 times 4 on the top, 10 times 10 on the bottom, and 16 over 100. A couple of things we can notice here. They're all out of 100. That suggests that there are 100 combinations in total. 100 different ways of combining these 10 counters. 36 of those options are a red then a red. 24 of them are a red then a blue. Another 24 are a blue then a red. And 16 of them are a blue and a blue. Something else to notice. If we were to add together 36, 24, 24 and 16, we would get 100. Now that makes sense because these are the only 4 combinations: red, 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 blue, blue, red, blue, blue, in different numbers, different likelihoods, different chances, but they are all of the options. So we should be getting 100 out of 100, i.e. 1. We are certain to get one of these 4 options. There are more probabilities we can find than just these, however. Yes, maybe we were interested in red then red, red then blue, blue then red, or blue then blue, but there are other ones we could find. For example, we could look at the probability that both the counters are the same colour. Now, both the counters being the same colour means that either we've got red then red, or we've got blue then blue. Now, when we're looking at red then red, that's 36 out of 100 chances. And when we're looking at blue then blue, that's 16 out of 100 chances. So it turns out that for these kind of probabilities, where we're looking at combinations of the ones from the ends of the branches, we can just add them together. Probability of red then red, 36 out of 100 chances, and the probability of blue then blue, 16 out of 100 chances. Altogether, that will give us 52 out of 100 options that are both the same colour. Something like probability of at least one red. Well, we need to look at each of the options that give us at least one red. Well, red then red will, red then blue will, and blue then red will. So those top three that we're looking at. We can add those together. Adding those top three together will give us the probability that we are looking at least one red. So we're going to have 36 out of 100 options, 24 out of 100 options, and another 24 out of 100 options, giving us 84 out of 100 options, 84 out of 100 chances in total. Now, in this question, the probabilities between first pick and second pick did not change, so it wasn't too difficult to fill in the branches. But what happens if we do change the circumstances between the first and second pick? What happens if we have an example where we don't replace the counter after the first pick? Well, let's have a look. A bag contains 7 green and 4 yellow counters. A counter is chosen from the bag at random, its colour is recorded, and the counter is not replaced. A second counter is then chosen. Well, this is where the probability tree really comes into its own and really proves to be useful. Because we're only ever considering one thing at a time, it is possible then to change the circumstances between the first and second pick. Once we've got all the numbers filled in on the tree, the rest of it just falls into place. The key thing is going to be drawing the tree. So we're going to start drawing the tree in the same way. We're going to think about the first pick first of all. Now, the first pick, there's 2 options, and those 2 options are green and yellow. We can fill in the probabilities for that fairly easily. There's 7 green and 4 yellow, so that's 11 counters in total. 7 of them are green, so we're going to have a 7 out of 11 chance of getting a green. And 4 of them are yellow, so we're going to have a 4 out of 11 chance of getting a yellow. So far, so good. Notice as well, 7 out of 11 and 4 out of 11 do add to make 11 out of 11, or 1. Now, let's imagine that the first pick was a green. If the first pick was a green, we've picked a green counter out, we've put it to one side. We're then going to pick another one out. There are then 2 options for the second counter out of the bag. The second counter out of the bag could be another green, or it could be a yellow. But this time, the probability of a green is not going to be 7 out of 11. Why not? Well, because there aren't 11 counters in the bag anymore. One of the greens has gone. So first thing to think about, there were 11 counters in the bag. One of the greens has gone. There are now only 10 counters in the bag. So our probabilities this time are out of 10. How many greens are there? There were 7. One of them has gone. There are only 6 left. So 6 out of 10. The yellows, there's still 4 yellows. But we're out of 10 this time, so 4 out of 10. And notice that those 2 probabilities add to 1. Let's imagine instead that rather than a green on the first pick, we got a yellow. There are then 2 options branching off from that for our second pick. Maybe the second pick was a green, or maybe the second pick was a yellow. Well, this time we had a yellow being taken out and put away. There were 11 counters. A yellow has gone. There are now 10 counters. So once again, our branches here are out of 10 rather than 11. If one of the yellows has gone, there are still 7 green counters. So the chance for green is 7 out of 10. But if one of the yellows has gone, there were 4 yellows, there's now 3. So we're looking at 3 out of 10. And again, 7 out of 10, 3 out of 10, add to give us 1. But now we've got the branches filled in, the rest of it falls into place. We can find the probabilities at the ends of the branches by just multiplying along the branches. So green then green, 7 out of 11 times 6 out of 10, 42 out of 110. Green then yellow, 7 out of 11 times 4 out of 10, 28 out of 110. Yellow then green, 4 out of 11 times 7 out of 10, following those branches along, 20 out of 110 again. And finally, yellow then yellow, 4 out of 11 times 3 out of 10, giving us 12 out of 110. Again, notice those two in the middle are the same. Sometimes that will happen, sometimes it won't. In this case, it has done. 110 options this time, because the act of not putting the counter back changes the possibility of what the second counter could be. The first event has an influence on the second. 110 options. 42 of those are green then green, 28 of them are green then yellow, 28 of them are yellow then green, and 12 of them are yellow then yellow. If we were to add those four numbers together, 42, 28, 28, and 12, we would get 110, and all of the options have been accounted for. And if we were interested in the probability of green then green, or green then yellow, or yellow then green, or yellow then yellow, then we're happy. We've found them all. As a note, it's always good to find all four of these, because if they add up, it's a good way of checking that we've probably done it right. The chances of getting numbers that work when they're wrong, quite slim. But maybe there are other probabilities that we want to investigate, other possibilities. We could, for example, work out once again the probability that both are the same colour. Well, that would be green and green, or yellow and yellow, and we're going to add those together. This time we're looking at 42 out of 110, and we're looking at 12 out of 110. If we add those together, that gives us 54 out of the 110 options that are both the same colour. Or maybe we want to look at the probability that they are both different colours. Well, that is us looking at green and yellow and green, those middle two. 28 out of 110 plus the 28 out of 110 gives us 56 out of 110 options in total. So probability trees are particularly useful if we are looking at multiple events. Counters in a bag is a classic, but it could also just be two unrelated events. One happening, then the other happening.